what a transition state is. So suppose I have some reactant valley over here. So this is a contour plot of my potential space V of R. And I define this position here. I call that the geometry of the reactant. Okay? And I have all these contours going up. And somewhere over here, I have another valley. Okay, so this might be my potential surface. So I want to know, here's my equilibrium geometry of my reactant. Here's my geometry of my product. And now, if I wanted to calculate the rate from the reactant to the product, a key issue is I have to define what's the dividing surface. And if I was looking at trajectories, suppose I started a bunch of trajectories all in this valley with different starting initial velocities, different directions, and slightly different initial positions all from this valley. And I just follow the trajectories. You know, some of these guys, I send them out here, and it comes up, and it wobbles around, and basically just stays in my valley for a long time. And some of them I start here, and it actually goes over here. Maybe it bounces back. And then maybe one of them comes up here, it skims off the wall, and it makes it to the product. Okay? So I have a lot of different possible trajectories I can start from. And the fraction of how many of these guys, these trajectories, end up at the product is proportional to the rate coefficient. You know, if the rate coefficient is high, then a high fraction of the trajectories will quickly get over to the product. If the rate coefficient is very low, most of them never get there, or else they take a really long time. Mostly they just never get there. And when I'm trying to assess where to put my dividing surface, I want to find the place where not very many things cross this dividing surface and turn around and go back. Because that means my assumption is going to be that I'm not going to have any recrossing when I compute the rate coefficient. So I want a dividing surface that separates it. So here, maybe I would choose the dividing surface to be something like this. You know, I have to get here. And so my idea is that this guy here, this narrow space here, is sort of defining the bottleneck on the reaction. But it's not so obvious, because it could be the bottleneck could be back over here, right? So when you have a complicated reaction, it's not always obvious where you should make the dividing surface. The more that your reaction approximates the sort of classical case, you have a reactant, you have a high pass that you have to cross, and then you go to product. This is like in the chemistry textbook. You probably saw this already when you were a kid. In this limit that it looks like this, basically trajectories will come up and fall back down, and then some of them have just enough energy and they just crawl over and they fall over. And there aren't very many that go across here and then turn around and come back up the hill to come back out. So the dividing surface is very accurately put right at the top of the saddle point. So for a high barrier reaction, then usually if you stick the dividing surface right at the saddle point, right at the top of the barrier, usually that's really good approximation. For a case like the potential I drew here, it's kind of flat in between these two guys, sort of like there's a high plane. So I climb up to a plateau, and I float around the plateau, and then I come down. A lot of times it's not so clear where the bottleneck is. And you want to draw the dividing surface, which is the transition state at the bottleneck. If you have a case where the reaction is slow, and most of the trajectories are turning around and coming back, which is a pretty common situation, because a lot of times chemical reaction is a rare event. It doesn't happen very often. In those kind of cases, you can kind of see that the system is basically equilibrated. I'm basically sampling all the space here in my reactant valley, and only once in a while is one of these guys leaking out through the bottleneck to get out. And so this is where the Eyring, when he wrote his paper, he said, oh, the transition state is in equilibrium with the reactants. And because it's way up at the top of the hill, the equilibrium concentration is very tiny. And then they're moving through at a certain rate. And he was able to derive the same formula for K of T using that point of view as you get from just doing the stat-mech physics trajectory method that I showed you. All right.
So that's a one product, one reactant.
Yeah.
How would, let's say, if I have H2 and O2, I know that I'm not just going straight to H2O. I might get an OH.
Yeah, that's a very good question. Yeah. So let's think. Let me think of a case like this. So if I have plus what? So HO2 plus OH. There's a couple different things that can happen here. One is like that these guys can glom together and make something that's sort of like HOOOH. And then this might break. It could go right back this way, or it could break the other way. So now you sort of transferred an O atom. Where suppose if it broke here. Also, these guys could go where this OH grabs that H. So it could go to, look, the transition state would look something like this. And that would go to H2O plus O2. Right? And I think there's even a way that this O could grab that H, and you could go to HOOH plus O. So there's multiple different possible product channels, even for just 4-atom system like this. If you get a complicated fuel molecule, like in gasoline or diesel or something, oftentimes there might be 20 different possible channels or more. And so then if you look at the potential surface, over, here is my reactants, which were HO2 plus OH. And in the middle here was the complex, HOOOH. And then there's sort of the symmetric products. HO plus OOH. And then somewhere down here I also got some other weird ones, right? HOOH plus O, and H2O plus O2. And each of these guys have their own valley. And then there's all kinds of mountains between these guys. So for example, there's a gigantic mountain between these two. You never, there's no way that, this is very complicated, right, to get from here to here. So there's no way. So the barrier is, 100 kcals or more. But the barrier from here to here is not that high because the OH bond strength is only a little bit stronger than this OH bond strength. So this is like this will be a mountain range, but it has a mountain pass in it. So there's some way through. You can wiggle through there. And this one is probably just all downhill. So if you bring these guys together, it just goes down, 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 down into the big, really deep valley here. And then this one comes right back up, no barrier at all. All right, and then I don't know, maybe this guy is connected to that one, yeah. So there's probably a mountain So another mountain range over here that has a pass. And this guy can climb up the valley, go through the pass, and come over there.
So you're just basically superimposing the different individual possibilities onto one another?
Yeah, there's one potential surface, so V of R, there's one V of R for the whole system of that number of atoms. And we have names for these valleys. Okay. And we would say giant mountain range here, mountain range with a pass here, mountain range with a pass over here, and then I don't know what's between here and here, probably another giant mountain range. And we would draw, and we could draw, so we could make an S, S for this reaction from here to here. S of R is equal to 0 for this particular S. And there's another one over here for this S, another one for this one, and for this one. And we might have trouble defining exactly where the S is here because there's no saddle point between these two guys, so they just attract directly. So in this case, we would have to do the variational approach because we wouldn't know where to put the dividing surface. So we'd have to try different dividing surfaces and see which one gives the slowest rate. For these ones where we have a mountain range with a little pass in it, we're pretty sure that the dividing surface should be right in the pass. So we just do that. Is that okay? And then somebody might come along and say, oh, you forgot one. And over here there's another isomer or another product, and then try to figure out how it connects to all the other ones. And my program RMG would automatically search for all the different possible products and then try to estimate all the different rates to some level of inaccuracy. And then it would compute them all and try to tell you which ones are the most important ones. All right. Yeah, something I didn't emphasize enough about the transition state theory that's really great is that to do this, all I needed to do is I need to know V of R at the valley for the reactants and at the saddle point. I don't need to know V of R at any other points. So contrast this to if I was actually trying to use trajectory methods to do this, I would have to know the potential at every point because the trajectories would go basically everywhere. And I'd have to compute V of R many, 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 many times. Now, if V of R is from a classical force field or somebody told me what it was, or look it up in a table, that's not a big deal. But if I have to run a quantum mechanical calculation to figure out the electron motion at every different nuclear arrangement, those calculations are very expensive. And so if I had to do it over and over again millions of times, that would make it really impractical. So that's a huge advantage because usually the V of R's are very expensive to calculate. And so this method where I only have to compute the V of R at 2 points. So I only need just these two special geometries are the only places where I need to know V of R. And then what people typically do is they only need to know V of R really accurately at 2 points. They would go get the most expensive, accurate quantum mechanical method they possibly could to get the very best numbers for those V of R's at those 2 points. And they come directly into the delta E. And that's because in the formula here, this energy difference between the reactants and the transition state comes in the exponent. So you really can't tolerate errors here. You need this to be as accurate as possible because whatever the error is going to be in an exponent that's going to really contribute. Whereas if you have errors in these terms, it's a lot less serious because it's just sort of linear. So if you're off by a factor of 2, you're just off by a factor of 2 in the rate. If you're off by a factor of 2 in this, you're dead. So anyway, that's a really nice thing about transition state theory. Now, let's talk about this for a second. So to compute the microcanonical K of E, I need to know these N of E's and the rho of E's, and here's the formulas for them. And this thing here can be kind of a problem because there's a lot of vibrational states. So this is quite a huge sum, actually. You have to sum over every vibrational frequency. And so if you have a big molecule, it might have 50 vibrational frequencies. And so this is like 50 nested summations. But these guys, Byers-Swinehart, found an algorithm that scales really well for solving that problem. So there's a way to add up this particular sum as a special sum that has a special trick for computing very effectively. So if you ever get into this, it's definitely worth your time to learn about this method. And there's a nice improvement on that for handling the non-harmonic modes by Astholz. You should read that paper if you ever get into this. Yeah, that's about all I need to say. Well, we'll talk about this in a minute. In principle, we've only kept track of E, but in principle, you should keep track of J as well, because J is the angular momentum of the entire reactants, and that's a conserved quantity because angular momentum is conserved. And the formulas that I gave, if you don't keep track of that, you're sort of violating angular momentum conservation in your calculation. It turns out that's usually not such a huge deal, so people do it all the time. It's just by luck. It turns out you can violate angular momentum conservation, the rate's still got pretty good. But if there's definitely a difference. You'll see you get a different number if you restrict all your summations to be things that conserve the angular momentum conservation. This is only important for the E case. So when you're doing the microcanonical, if you're doing canonical, you're assuming there's a lot of collisions with the bath gas to keep you in thermal equilibrium, and presumably you're also scrambling the angular momentum quantum numbers like crazy too, because you're having a lot of collisions. But if you're assuming the microcanonical case, that means you're assuming that energy is conserved for a long period, a long enough period for the reaction to occur. Presumably angular momentum will also be conserved for about the same period. All right, so almost everybody uses the formulas I showed you. These rigid rotor harmonic oscillator Qs in the transition state theory formula, and that's how you get the rates, and it works pretty well. So there's several problems. So one problem is anharmonicities. So the rigid rotor harmonic oscillator is not accurate for thermo, and it's even worse for rates, because at the saddle point, oftentimes the potential is really anharmonic. You can try to, if you know what the anharmonicity is, if you know the shape of V of R, you can try to put this in. And there's a nice paper here that compares different methods for trying to include the anharmonicity in the rate. There's a Monte Carlo way of trying to evaluate these Qs. In classical mechanics, that works great. So you can use Monte Carlo with classical mechanics and get a really good correction for Q. For quantum mechanics, people don't know how to do it so well. So what they usually say is, let's assume the classical correction for anharmonicity is the same as it is for quantum, and because it's easy to compute. And so you can do that. Checking whether your approximation is accurate or not might not be possible or might be too hard to do. But at least you can do it. And you get an idea. If the anharmonic effect is really small classically, probably it's small quantum mechanically. But if it's really big classically, it might be big quantum mechanically too. Who knows? So that's sort of a challenge. Pitzer-Gwynne was sort of the same thing. He said, well, let's calculate some things classically and do some ratios of classical numbers and multiply them by the quantum mechanical number. And that's, again, it's done a lot. It works for some cases. I think people don't know. There is a way to try to include the anharmonicity in the calculation of the integrals. It's really expensive and people don't usually do it, but there's a lot of interest in trying to be able to do it. And if you're really into it, the anharmonicity, there's two different kinds of anharmonicity. One is that if I look at V as a function of like one bond length, it's not really a parabola. It really might be the shape of a Morse oscillator or something like that. So for example, if I have OH, I can write the potential energy as a function of the distance of the O from the H. And the real shape of this is something like this. But if I approximate it with my rigid rotor harmonic oscillator, I might use this. So I'm using this dotted line to approximate the potential when it really is like this. Obviously, it's not right. And so there's a way to correct for this. That's one thing. A more complicated problem is that in a big molecule, you have multiple vibrations. And when the one bond stretches, it actually affects the potential for the other bonds. And you also have couplings between them. So it's sort of like you have a system of springs. But if you pull like one spring in a system, other things might start vibrating, right? And so the same thing can happen in the molecule. If you wiggle one end of the molecule, after a while, the other parts start wiggling because there's sort of anharmonicities coupling them all together. And trying to know what to do about that is not so easy. There are programs, for example, this thing called multimode, which explicitly puts in all the anharmonic couplings of all the vibrations, and then solves the whole Schrodinger equation for the vibrations to figure out what the corrected zero-point energy is and what all the corrected energy levels are. And it's interesting, and I actually spent a couple years of my life working on this, but I would say it has not caught on mainstream because you need to know a lot of information about the potential surface to know all the anharmonicities correctly, and also this calculation is kind of expensive. And then you end up with a zillion energy levels, and you have to somehow compute the partition functions of that thing. People don't know how to do that very well either. So this is sort of for some small molecules, people have done a nice job with this, but it's not really general purpose yet, I would say. But it's the kind of thing that it could be automated and could be made to be general purpose. So maybe in the future, this will be a way to do it. The particularly type of anharmonicity that's the most important and the most trouble for us is torsions. So we have a lot of fuel molecules that have CC single bonds. And every time you have a CC single bond, you usually can have a pretty free rotation of the molecule around the CC single bond, very slightly hindered. And that is wildly different than a parabolic potential. There's no relation to it. To get into this, you have to worry about, first of all, there's like internal moments of inertia. So one piece of the molecule is rotating relative to the other pieces. It's like a Ferris wheel or something. And so you have to know what the internal moment of inertias are. And then that couples to the external rotational motion. So the entire molecule is wiggling around, spinning around. And meanwhile, the Ferris wheel is going. And it does something wild with the angular momentum. And so there's angular momentum conservation rules, and you get special effects on the moments of inertia. And so this paper by East is very famous as clarifying some of the details about that. There was actually a bunch of previous papers by Pitzer a long time ago that it gave the formulas for a lot of common cases of how to handle it. Then there's this question of how to evaluate the Q. Again, a lot of people would do the classical thing, where you just evaluate this integral classically and then hope that the quantum effects are small. And it's very practical because you can do it. But again, the accuracy is not so known. And then people would do the Pitzer-Gwynn approximation, which is to do the classical correction and then multiply it times the quantum mechanical result. A general problem is if you have multiple torsional modes, you have several different things rotating around at once, like several Ferris wheels hanging off at different angles. They can be coupled to each other, and in fact, they all usually are. And so that turns out to be a big headache. And so if you want to read about that, I have a paper showing how big this effect can be. So this gives maybe about a factor of 10 effect on the rates in some temperature regime. These guys have a method for how to incorporate the anharmonicities into the partition functions and into like derived quantities like the heat capacity. And so if you want to do better thermochemistry, you can follow their method. And whenever you have a paper that ends with a question mark in the title, that means they don't know either. So, but it's usually very interesting to read because somebody's not going to write a paper like that unless they think we really have a big problem. And so, this group in Belgium has done a lot of work on trying to figure out how to do it. And in cases where the coupling is not too strong, then there are good methods of how to do it. But if the coupling is strong, it's really difficult to accurately calculate the energy levels. But it often turns out that your rates you calculate using stupid approximations are pretty close. So I think there's like a huge compensation effect that although these things are coupled, the total number of energy levels is about the same. And the total number in this energy range are about the same, even though the actual energy levels that the molecule are different than the approximate energy levels we're using when computing the partition functions. It sort of averages out by luck. But of course, by Murphy's law, the case you care about will be the one where it doesn't work. Right? And variational transition state theory is a big topic. So the conventional transition theory works really great for molecules with high barriers. And it's easy. And everybody knows how to do it now. And there's semi-automated programs that do it for you. And you can get great rates. But then the variational ones, in general, people don't know how to do it so well, and it's more expensive because you don't know where to do the calculation of the barrier height, because there is no barrier, typically, or there's a very flat surface and not a clear place where the bottleneck should be. And so then you have to do a lot of calculations because you have to try a lot of different trial locations for the dividing surface. Each of those needs a high accuracy calculation of V of R. And often this happens in cases where the barrier is pretty small, which means that the error in your quantum mechanical method might be bigger than the whole size of the barrier. So then you have to use a pretty accurate quantum mechanical method to do your V of R calculations, but that makes the expense goes up. So it ends up you have to do a lot of expensive calculations instead of doing just one expensive calculation, which you would normally have to do. And so this is a big problem. A guy...
Is it usually guaranteed that a minimal can be found?
Well, if you only try n dividing surfaces, one of them will have the lowest.
But if you move from A to B, if you move from A to B, you find a minimum, right?
Normally you will not be at the true minimum. Normally you just be at the... Sorry, I'll repeat the question. The question is there any guarantee that you'll actually find the bottleneck, that you'll actually find the minimum rate? And there is no guarantee. And beyond that, you never do. You just try some, and you find some dividing surface that gives a lower dividing value of the rate than all the other dividing surfaces you tried. And at some point, your computing budget runs out, and it's time to write the paper, and you just stop, and you just publish that one. Okay? And it's worse than that. It's one of these things where you don't even know, there might be more than one minimum. You don't know how many minima there are. There's no proof. There's nothing about the topology that will tell you, typically. It's a typical nonlinear algebraic equations problem. So you don't know how many minima there are. If you find one, you don't know if it's the lowest one. And you're just stuck. So this is one reason. Many people just don't like to do these calculations at all because it's just fraught with trouble. However, some guys are brave. And particularly there's a guy whose name should be on the slide but didn't appear, Klippenstein. And he sort of invented the best methods for doing this and has done the best calculations like this. And there's many good calculations by him for reactions with no barriers, where he's able to compare them to experiment, and typically maybe within factor of 2 of the experimental rates. Now he's still off, so it's no guarantee, and his method is definitely not guaranteed to be right either. But experience is normally you can do it pretty well. But it costs maybe 100 times, 1,000 times as much CPU time as a normal conventional intrinsic theory calculation. So that's why a lot of people just say forget it. I'd rather do 100 regular reactions than do one oddball one that's going to take us so much time to do. But if you're somebody like Klippenstein, you want to do the bold, difficult thing. And you also, if you're going to do all that effort to get all these calculations, you might as well try to do the best job you can. So then you might include the fact that the angular momentum is conserved as well. And so some of Klippenstein's papers in particular, but also these guys, have papers about this. Tunneling. So in quantum mechanics, you do not have to go over the barrier. You can just go through the barrier. And that's kind of strange. And so this is a way that you can sort of beat the Arrhenius-Boltzmann restriction on rates. And this is particularly important at low temperatures where you don't have any Boltzmann population with enough energy to really do the reaction. Then even a very small amount of tunneling rate might be the dominant thing. And so this is typically what you see if you plot the log of k versus 1 over t, is that we would calculate something that would look not quite Arrhenius, but pretty much like Arrhenius. And then if you put the tunneling in, it looks the same at high temperature, but then it deviates and gets faster and faster at lower temperatures. So for room temperature and below room temperature reactions, usually you have to worry about the tunneling. It's very important. And particularly in cryogenic, like if you do something liquid nitrogen temperature, the tunneling might be everything. But if you're at combustion temperatures, usually it's a small correction, maybe 10% or less correction. So a lot of times combustion people might not even worry about it. But if you're trying to compare your prediction to experiments done at room temperature, there's a lot of data at room temperature, then you need to put it in because otherwise you won't match correctly with the room temperature experiment.
So the reason for that is a low temperature because no particular rate energy
The reason why it's more important at low temperature? Yeah, so why is this more important at low temperature? The reason why it's more important at low temperature is that the Boltzmann tail is very thin at low temperature. You have very, very few molecules with the high Boltzmann energies. So you have almost all the molecules have energies way below the barrier. And so if they have any way to sneak through the barrier, there's a million of them, but there's only one molecule that's above the barrier. So that guy reacts, but if there's a million of them that each have one chance out of a million to get through the barrier, then they might be able to be just as important as the. And as you go to lower temperatures, you don't have any molecules or very, very tiny numbers that will be above the barrier. I really, if you're 4 degrees Kelvin or something. And so then it'll all be the tunneling. There's actually a pretty fun case that's important in combustion. There's a really strange molecule, H and N, and this is not very stable. And what the potential energy looks like so the H atom, this is the R for the H atom from the N2. It looks like this. So here's H plus N2. Here's HNN. And in this case, you can have a situation where even the ground state, the V equals 0 state, the tunneling rate is significant. And so this one, even in the ground state, is just going away. But it means it also can go back. So when an H atom comes up to an N2, even if it doesn't have enough energy to react and go across the top here, you can still get some probability that it makes HNN. And this HNN lives for a couple nanoseconds, and then it falls back apart by tunneling again. But if during that time an O atom comes up, then they can react, and they'll make NH plus NO. And this is actually a significant source of NO in some hydrogen flames. So this is pretty funky. But this is atypical. So usually in combustion, the tunneling is not really such a big deal. This is one of the rare reactions where it's the dominant path.
So, trying to conceptualize what quantum tunneling is, if you have a potential surface, is it a fourth-dimensional manifestation of the reaction path?
I think that the way I think about it, this is totally non-classical, right? So trying to think about it is weird. But the way I think about it, for what it's worth, is suppose I just had this case I had there. This ground state, vibrational state, it is actually a wave function. The reason why I have a 0-point energy is that we don't know where the atoms are. We don't know where the H atom is because of the Heisenberg uncertainty principle. So it has a probability of being each different location. And when you solve the equation, these tails of the probability distribution for the H atom actually extend out into the non-classical region and a tiny bit of that tail extends all the way through to the other side over here. And quantitatively, you have to solve the wave equation to see what it is. But that's what it is. It never actually goes to 0. It's like anything is possible in quantum mechanics. Yeah.
Is the fraction of the molecules that goes through this tunneling a function of temperature?
Yes. So is the fraction of the molecules that go through tunneling a function of temperature? Yes. So if the barrier is low enough and the temperature is high enough, everything will react over the barrier really fast. And you won't have time for many of these guys to tunnel through. Because the tunneling, another way to look at the tunneling is that this guy is vibrating back and forth, chung, 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 like back and forth. And every time it has a chance, like one chance out of a million of going through. But most of the time it doesn't. It just bounces back and forth like a regular classical particle in a well, back and forth. If during this time it's bouncing back and forth, it suffers a collision with the bath gas that gives it some extra energy and it gets above the barrier, then it's just going to go flying out. And so it's like the relative rate of how fast is this being knocked up to fall out compared to how fast it's leaking through. And so at higher temperatures, the bath gas has a lot of energy, and one collision of bath gas might be enough to knock it over the barrier and it falls out. So at high temperatures, it might almost all go this way. But at low temperatures, it might just sit there and all of them will leak out that way. And in fact, people do experiments in liquid helium-cooled cryogenic things, and then they'll see the tunneling is actually very significant. You make the stuff, and you look at it a while later and it's all gone. It's like, where'd it go? It was a 4 Kelvin. It couldn't, you can calculate the thermal rate is like 0. And it's all because it's all quantum mechanically tunneled.
But you need to also consider the non-classical reflection.
Yeah. So yeah, in quantum mechanics, in classical mechanics, you get up to here, this energy, and you come off here and you go out, and it all goes out. But in quantum mechanics, you have a 1 chance out of 1,000,000 that it might actually pop back. Actually, it's about 1 chance out of half that it'll go back. So quantum mechanics is weird. It can reflect even if it doesn't actually hit anything. Quantum mechanics is very strange. But it's because the particles are like waves, so they're sort of feeling things that not right where they are. It's not local. It's like spread.
Only hydrogen tunnels or another kind of atom?
Everything tunnels, but the tunneling rate goes as the mass. Does anybody know what power? I don't remember. Anyway, it's a pretty high power, the mass. And so the hydrogen tunneling is like tremendously higher than all the other molecule tunneling. And in the, maybe I'll bring it next time. There's a formula to give roughly how it scales the tunneling. And it's like the inverted frequency of what this parabola shape is. And that inverted frequency is always much, much higher for hydrogen motions than for anything else. So even going from hydrogen to deuterium, you'll see the tunneling rate will drop a lot. Though I think you could still see it a little bit in deuterium. If you have muonium, we use muons instead of hydrogen, then you can see really gigantic tunneling. All right. We should stop pretty soon. So the tunneling correction. So here we go. Here's the formula I was just talking about. So this is the simple perturbative formula for what the tunneling rate should be. And it's this imaginary frequency, the upside down parabola frequency. It comes in here, and it comes in squared over kT. And so this is a very simple thing to calculate, because when you do the normal mode analysis for the saddle point, you'll get one negative frequency, and all the others are positive, because there's one negative curvature direction for saddle point, and all the rest are positive. And that negative frequency you get from that analysis is this nu you need to put in there for the tunneling. And you can just evaluate this thing. If this number, if this part here is anything close to 1, then tunneling is significant. If it's much, much less than 1, then you don't have to worry about it. If it's close to 1, this formula breaks down because it's a perturbation theory. And then you have to go and use fancier methods. A pretty good method to use is Eckhart method. However, if you do use Eckhart method, make sure you read a lot of papers, because the most famous quoting of the Eckhart method had a typo in the equation. And so actually a paper by Professor Trular found the mistake in the textbook and gives a correction. If you don't find the citation to that, you're in trouble, because many, many people quoted the wrong number over and over. So there's like 1,000 incorrect equations in the literature for Eckhart. If you really care about it, so if you go to lower temperature case, and the tunneling is very important, there's a nice program called Polyrate, and it has several different methods for computing the tunneling, including multidimensional effects. So in the real system, it's not just moving in one direction. The molecules are wiggling every which way. And correcting for all that multidimensionality of the problem is complicated to do, but the Trular group has developed methods to do it, all these guys here. They're better than these methods, but I would say all these methods are like not perfect also. So all these things are approximate. But many times in your cases, you'll find out that all the methods will say your tunneling is negligible, and you don't have to worry about it. And then if you do have to worry about it, then you want to go and become an expert in these methods and learn about what they can tell you. And if you try different methods and they really differ, then you should warn you that there's some big problem that you should pay attention to. And you can download this software here. This software also computes other things besides tunneling. This is a really nice general purpose software for kinetics. Here's a picture of what happens. So the normal method, Wigner's, you just do a perturbation theory expansion at the saddle point, and you move like a straight line here. But the real tunneling actually can happen like this, where the molecule is coming along and it just goes through the barrier over to there, like that. And so you want to get this multidimensionality, the fact that it's sort of curved. You have to do it with something like SCT or OMT methods, these guys. All right, summary. almost everything that we would ever do would start from the Born-Oppenheimer approximation, and we would use the V of R's that we get from quantum chemistry code. The predictions are going to depend very crucially on how accurate those V of R's are. And this is a big problem. And historically, this was always the biggest source of error. In recent years, some of the quantum methods have gotten so good that this is no longer the biggest error. And instead, it's just comparable to a whole bunch of other errors in the approximations. The V of R, the biggest error is the error in EA. And so a lot of times you might believe the A factor from a quantum mechanical calculation more than you would believe the EA. However, if you have torsions, a lot of torsions, then you might worry also about the A factor being significantly wrong because your partition functions are wrong for the vibrations. The classical mechanics can be transformed into the quantum mechanics, and there's proofs that it's true, but usually the exact quantum mechanics equations are too hard to solve. But there's some nice simple approximations to convert classical mechanics into the conventional transition state theory with sort of semi-classical corrections. This turns out to be much, much less expensive to compute and still be pretty accurate, sometimes better than a factor of 2, almost always within an order of magnitude of the true rate coefficient. And so this is by far the most popular thing to do. Some of these approximations are not really that good, which is why we have these sort of order of magnitude errors sometimes. And so people are working on fixing the tunneling, the anharmonicity, the recrossing, many different small errors in the conventional transition state theory. And so that's an active field. A lot of people in research in the theoretical kinetics are working on trying to make better methods for that. And I think I will just stop there. So thank you, and we'll see you next time.